Look at this sentence. This statement cannot be proven. Seems harmless, right? But think about it. If we can prove it, then it's false. We just proved something false. If we cannot prove it, then it's true, but we can't prove it. In 1931, a 25-year-old logician named Kurt Gödel turned this simple paradox into pure mathematics, and in doing so he destroyed the greatest dream of the 20th century mathematics. This wasn't just an abstract puzzle. Gödel's discovery changed everything: how computers work, whether AI can ever be truly intelligent, the limits of human knowledge itself, and whether your mind is just a very complex machine. By the end of this video, you'll understand why one of the most brilliant ideas in human history is about what we can't know, and why that's actually beautiful. But first, we need to understand what Gödel broke. The year is 1900. David Hilbert, one of the greatest mathematicians alive, stands before the International Congress and announces his vision: to build a complete, perfect foundation for all of mathematics. Here's what complete meant. Complete. Every true mathematical statement can be proven. Consistent. No contradictions can ever arise. Decidable. An algorithm exists to determine if any statement is provable. Think of it as the ultimate instruction manual for reality. A finite set of rules from which every mathematical truth flows inevitably, like a perfect machine. This wasn't arrogance. Mathematics had been shaken by paradoxes in the 1800s. Hilbert wanted to eliminate uncertainty forever. Many believed he'd succeed. After all, 2 + 2 = 4. Not sometimes, not approximately, always. Mathematics seemed different from the messy human world, pure, eternal, provable. They were about to discover they were wrong. Enter Kurt Gödel. In 1931, he publishes a paper with a modest title, On Formally Undecidable Propositions. The content was anything but modest. First, Incompleteness Theorem. In any consistent formal system powerful enough to describe arithmetic, there exist true statements that cannot be proven within that system. Let me say that differently. True, but unprovable. Now here's where it gets brilliant. How do you prove something is unprovable? That sounds impossible. Gödel's genius was embedding that paradox we started with. This statement cannot be proven, directly into mathematics itself. He invented something called Gödel numbering. Every mathematical symbol becomes a number. Every statement becomes a number. Every proof becomes a number. Then, using these numbers, he constructed a specific mathematical statement, let's call it G, that says, in the language of arithmetic, statement G cannot be proven. Now watch what happens. Scenario 1. Suppose we can prove G. Then G is true. We proved it. But G says G cannot be proven. So we've proven something false. The system is inconsistent. Scenario 2. Suppose we cannot prove G. Then what G says is actually correct. G is true, but we cannot prove it. The system is incomplete. There's no escape. Any sufficiently powerful mathematical system must be either incomplete or inconsistent. You cannot have both. Okay, I know that was dense. Let's make this concrete with something we can actually picture. Take something called the Continuum Hypothesis. It asks a simple question. Is there a set size between the integers and the real numbers? Mathematicians wrestled with this for decades. Then, in the 1960s, Paul Cohen proved something shocking. The Continuum Hypothesis is independent of standard set theory. You can assume it's true and get consistent mathematics, or assume it's false and get consistent mathematics. Both work. The question exists outside the system's rules, like asking whether a chessboard should be wooden or marble. The rules of chess don't care. Both are valid. This is Gödel's legacy. Mathematical truth is richer than mathematical proof. Now here's the crucial point. Gödel did not break mathematics. Your calculator still works. Engineers still build bridges that stand. Physics still predicts reality. What changed was our understanding of what mathematics is. Think of formal systems like games. Each has rules. Gödel showed that no matter which game you play, if it's rich enough to be interesting, there will always be questions the rules cannot answer. This doesn't make mathematics useless, it makes it infinite. Gödel's insights didn't stay in pure mathematics. They rippled outward. Alan Turing, inspired by Gödel's work, proved the halting problem. There's no algorithm that can determine whether every possible program will finish running or loop forever. This isn't a limitation of current technology, it's fundamental. Some questions are uncomputable, just as some truths are unprovable. And here's where it gets philosophical. If your brain is a computational system, neurons firing according to rules, do Gödelian limits apply to you? Can humans know truths we cannot formally prove? Is consciousness the thing that escapes the system? Or are we bound by the same limits? These aren't settled questions. Gödel opened doors we're still walking through. Here's what makes Gödel's theorems beautiful. The ancient Greeks believed mathematics was about discovering eternal truths, a perfect, complete universe of knowledge. Hilbert wanted to systematize those truths, to build the ultimate map of mathematical reality. Gödel showed that the territory is forever larger than any map we can draw. This is not a failure, it's not a limitation, it's an invitation. Every theorem we prove reveals new, unprovable truths waiting beyond. Every answer opens new questions. Mathematics isn't a finished cathedral, it's an endless landscape. And perhaps that's exactly as it should be. The universe didn't promise us complete knowledge. It promised us something better, an infinite frontier. In trying to perfect mathematics, we discovered something more profound. Mathematics that can never be exhausted. Truth that exceeds proof. And certainty about uncertainty itself. That's Gödel's gift. Not the limits of knowledge, but its limitlessness. And here's the wildest part. Gödel himself spent his life grappling with the paradox he'd discovered, a man who proved that even perfect logic has boundaries, trying to live with that truth. That's a story for another time.